In this video, I'm going to show you a very powerful programming technique of using functions and storing them in tabs as a way of organizing your sketches and your code. And here's the basic method that we're going to use. You know, the normal structure is we have variables at the very beginning, and these variables are going to be used throughout the entire sketch, the main loop, including the functions. The next piece is the setup, and this is going to be the same thing. It's going to set up any of the hardware features that or software features that we want to set up. This will be executed very first, and then we have the loop. And in the loop, the only thing that should be in the loop are a few operations and then functions. And so all the code is really contained in functions. And we're going to place the functions in tabs. And to illustrate this, we're going to look at a specific operation that we want to perform. We want to measure the time it takes to execute a particular code, like a digital read or like a digital write. How long does it take to actually execute that command? And here's how we're going to do it. We're going to set up a function in a tab, and we're going to do it there. And so here's how we do it. You notice at the very top of the screen here, off to the far right, the little pull down arrow. So we are going to pull that arrow down, and we're going to create a new tab. And it's in the tabs that we store the functions. And when we save the sketch, the functions will be saved as separate lines or separate files that will be called by the main loop. So very simple. We create a new tab. We're asked to name it, and we're going to call the name of the tab. You know, my preference is anything we want, but I'm going to make it the name of the function. They're two completely different things. One is the function that is called. The other is the name of the tab. But to make it easy to keep track, I'm going to use the name of the function. And I like to identify a function by using the prefix funct and then an underscore, and this is going to be timing. And that's going to be the name of the tab. So say, okay, and look, we've got a new tab. And this is more code that we can write. And I'm going to create a function here. The very first line, I like to use just the kind of the name of it and what it's going to do. This is going to measure the execution time for some code. The next line is going to be creating the function. And you always start with the type of function it is. Void means nothing is returned directly. I like to use the variables to transfer information back and forth. And the name of the function, I'm going to type in the function as the beginning, and this is going to be, I'll call this timing. This is the name of the function. You need little parentheses here. Nothing's going to be returned through it. And then you start with the brackets, and we're done. Everything about this function is going to be contained in here. We're defining the function. And here's the algorithm that we're going to use. I'm just going to type the algorithm in here. We're going to measure the initial, we're going to time things by using the internal clock. So the initial time, and that's using the microsecond timer that's built in. Then we're going to build a loop and execute function many times. We're going to stop the clock. We're going to measure the total execution time. And then we're going to divide by number of iterations. That's it. Really simple. Now, one important thing about variables that we're going to move in both forms. When we're in the main code, any variable that we define at the beginning is global in the sense that it applies to the main page, and the same variables have been defined and are used and can be used throughout any function. But if I define a variable in a function, that is, has to be within this function here, it becomes local and only stays locally. And I can use there's no information about that function that carries through anywhere else. I have to use a different name for the local variables than I do a global variable. Only thing to watch out for. So let's begin. It's really going to be straightforward. So I'm going to measure initial time. I need to create a new variable. This is going to be a long. This is going to be, I'll call it, and I like to use a letter I if it's an integer, if it's not obvious. So this is going to be time 0, that's the start time. This is going to be in units of microseconds. Let's see, and then we're going to look at, we're going to do a digital write. And we're going to see how fast we can toggle digital write on, off, on, off. So we're going to do that 1,000 times. So here's our loop. We're going to do a for, and here's our index that we're going to move equal 1 until that number, that index is, well, it's still greater than or equal to 1,000. We want to keep going with the loop. And in that loop, we're going to do a digital write. And let's see, which pin will we use? We've been using pin 0 for the DAC, pin 1 for the ADC. Let's use pin 2. And so we'll do a write, pin 2, and this is going to be turning on a high. Now, in order to use a digital pin, we need to declare it as, hey, we're using this digital pin. And we can declare it anywhere. We can declare it in the global section here, or we can declare it in the function as well. And so let's do that in here. So we're going to do pin mode of pin 2, and this is going to be an output. And we also want to turn it off. So it's going to be a digital write, pin 2, a low. And so literally we're going to toggle it off and on, off and on, off and on. And then we're going to measure how long it takes. So right at the beginning, before we start this loop, let's measure the initial time. I time 0 in microseconds is the value of the microsecond timer, which is the microsecond timer. That tells me the start time. By the time we're done here, this is the stop time. I want to know, okay, how much time has elapsed? And I want to divide that by the number of iterations. And I'm going to put that into a new variable, and that's going to be the execution time. Now, because we're going to get a fraction of a microsecond here, I want to use a float to define that. So it's going to be float of execution time. That's going to be in units of microseconds. And that is literally going to be execution time in microseconds is the total time, which is the time now, minus the start time in microseconds. And this needs to be a 0 here. So this is the total execution time for these 1,000 steps divided by 1,000 steps, but I want it to be floating point so that I get the fraction of a microsecond. And I'm done. And then I want to print this out, and so I'm going to have a serial.print, and since it's the only thing I'm printing out, I'm going to put a line feed after it, and this is going to be execution time in microseconds. Now, I'm using just 1,000 iterations. I could do 10,000 iterations. I have an integer here, so I've kind of limited myself to 16,000, but I could easily do 10,000, and we use 10,000. The more we do, the more accuracy that we're getting, because we're using a microsecond. Actually, it's it's about a microsecond as the step size, and if we do a lot of iterations, we'll measure a longer amount of microseconds, so we'll get a little better accuracy. And we're done. And so we're going to execute this print within the function. Now, to clean it up and make it look a little neater, I like using tools and auto format. And this told me, uh-oh, I forgot. I needed a little semicolon over here, so let me do it again. This is another reason why the auto format helps a lot. And so here's what we got. We're going to measure the execution time. Here's my the algorithm. I've defined this variable, defined that variable. I've set the pin 2 as an output, initialized the timer. We're going to iterate for 10,000 times. We're going to turn it high, low, high, low, high, low. And then we're going to look at it on the scope as well. And then we're going to look at the total time to execute is this time divided by the number of iterations. So that's the execution time for one cycle. And we're going to print them out. And that's it. So in order to run this, I need to take our function over here and I need to call it from the main loop. So let's go to the main loop. So I just copied that, go to the main loop. Now I'm not going to do any of these things here. So here's the setup. And it's perfectly fine to keep this in here. It's not going to be a problem. And it's in the loop here that I'm going to put the function. And I'm not going to do the analog right here. So I'm going to comment these out as well. So right now there's nothing in my loop. All I'm going to put here is my function. And we need a semicolon. And so how do I know this is a function scenario? Well, I get the parentheses here, that's a giveaway, but it's also my labeling scheme. I'm calling out specifically, hey, this is a function that I've got here. And every time the loop runs, that function is going to run, and I'm going to print out on the serial monitor what the execution time is for doing the high, low, and we might be able to see that on the scope. So we're ready to go, and I'm going to upload. So compile, compile, compile. We're saving that additional code there as we upload, and okay, we open up that file, done uploading, and now if I open up the serial monitor, here's the execution time in microseconds. It's 2.92 microseconds. You know, if I wanted to get a few more digits on it, I would go to my tab, and when I print out the execution time, the default is 2 decimal places. Let me make it 3 decimal places, so I'll get it to within a nanosecond. And we'll upload the code, and then we'll look at the COM port. And here we go. So it's 2.918 microseconds. Now, if I was really clever, I could say, how many clock cycles is that? Because after all, I know the clock is 48 megahertz. And so this is in microseconds. And so if instead of typing the execution time, I say, hey, I know I have 48 cycles per 48 microseconds per cycle in the clock. Hey, tell me how many clock cycles it is to execute that code. So I multiply by 48. So here's microseconds times megahertz. So that's units of cycles. So we upload that code, and now we'll get the number of clock cycles to execute the code. So this is 48 megahertz is the clock for the SAMD21 in the Xiao module. And should be able to see, there it is. Hey, it's about 147 clock cycles is the time to execute write and then turn it on and turn it off. Going back to the time, let's see, it was 2 microseconds, so we ought to see about 500 kilohertz or so as the toggle frequency. So let's go ahead and set up our scope. We'll measure the voltage on pin 2. And here is the measured voltage on pin 2. First we'll look at the COM port. There it is, 2.9. So 2.9 microseconds. So let's see, that's about 3 microseconds. About 300 kilohertz is what I expect to see. So here's that signal coming out. Let's adjust the time base a little better. Let's see. And so we're about 2 microseconds of division, and we've got 1 cycle, 2 cycles, 3 cycles, 3 cycles in about 1, 2, 3, 4, 8. I got 3 cycles in about 8 microseconds. So hey, that's pretty close to about 3 microseconds a cycle, or roughly what we kind of measure here. And we can have the scope measure for us. Now that we have a rough idea what it is, we'll have the scope measure for us what that frequency is. So we'll come over here to measurements, and hey, and there it is. The frequency in channel 1 is 345 kilohertz, just about what we expect to see. And now we have a precise numerical value for that execution time. And so let's think about what we've got here in the code. We can put any function that we want in here to calculate its timing, how long it takes to execute. We can put the an analog read, for example. So how long does it take to read a signal from port 1 or channel 1? So let's try that. Analog read, and that's going to be in port 1. And all we're going to do is ask, okay, just go read it. We don't even have to put it to a variable if we don't want to. That might add a little bit more time to it. But let's try this. It's just going to go out and read what's on the ADC channel on port 1. So let's execute that, and then we'll look at the printout from that as well. So the only thing that's going to be in this loop is go read that the channel, and then tell us what the execution time is. And so here is the COM port. Hey, 14.3 microseconds is the time it takes to read an analog signal. And if I wanted to, I could say, well, okay, let's set that to let's create another long variable here. Again, this is all local. This is going to be the voltage on the actually we already have a variable to read the analog channel, right? This is going to be the voltage on the analog channel 1 in ADU. And that's equal to this. And so whether we assign it to a variable or not shouldn't take any additional time. Remember, we declared this in the main loop. There it is in the main loop. And so it's a global variable. That's how you pass information. Simple way from a function to the main loop is to use a global variable, because all we're doing is changing the register value for that global variable in the function. We can still read it in the main loop, and we can pass global variable values between different functions. So let's run it, and remember it's 13 microseconds just read the analog channel, and now if we assign it to a variable name, let's see how much longer it takes. And okay, 14.4. Hey, there was an additional microsecond to do the assignment of that variable or that analog value into the register value for that variable. So this is how we can measure the execution time for any operation at all, and we've done it as a function, and it's not cluttering up the rest of our loop. That's going to be the way that we write clean, manageable code. We use functions to do that. Okay, so in the next video, we're going to walk through taking a collection of data and displaying it on the serial plotter.